This is Google's VO3, a state-of-the-art video generation model. It certainly took some creative liberties. There's a really weird Transformers situation over here. And what's up with these bunny jumps? General video generation models still don't have a good grasp of real-world dynamics. They understand some physical laws like gravity or object occlusion, but they can't clear the quality bar required by production systems like autonomous vehicles. For that, I hear we need something else.
The world model.
World models.
The world model.
The world model.
Okay, fine, let's try one. This is Genie, Google's world model. It seems like world models might actually work. Now look, this buzzword is being thrown around in all kinds of contexts today as some sort of big unlock in the pursuit of AGI. And a lot of us are left wondering, what exactly is a world model? How do you build one? And then what do you do with it? In this video, we'll try to clear out this confusion. We'll go through the definition, implementations, and the many applications of world models. We'll also hear directly from TJ Galda, an expert from NVIDIA leading their world model efforts. But first things first, what exactly is a world model? The idea dates all the way back to 1943, when a Scottish psychologist named Kenneth Craig suggested that the human mind has an internal, small-scale model of reality.
It can try out various alternatives, conclude which is the best of them, and act in a much fuller, safer, and more competent manner.
It's how you know that jumping in front of a train is a bad idea, even if you've never tried it before. About 80 years later, in 2018, a paper called World Models brought this idea to machine learning. An agent learning to play a variation of Doom leverages a small internal model of the game to imagine how its actions would play out in the real game. Today, prominent researchers agree that world models are essential to building AI systems that can plan, reason, and act safely in the real world.
Imagine a cube floating in the air in front of you, and imagine rotating that cube by 90 degrees. You can sort of picture this in your mind, and this has nothing to do with language. Humans and animals navigate the world by building mental models of reality. What if AI could develop this kind of common sense, an ability to make predictions of what's going to happen in some sort of abstract representation space? We call this concept a world model.
In the strictest sense, in the context of machine learning, a world model takes in the current state of the world, together with a hypothetical action that could take place in it. Its goal is to predict the effect of this action, reflected in a future world state. This is the interface that is most faithful to the roots of world models in cognitive science. What's your minimal definition of a world model?
When we say world model, we mean an AI system that literally learns and how the physical world changes over time, right? And so in the same way a language model can predict like the next token or, a syllable of a word, essentially, a world model is really predicting the state of the world. Not just what it looks like, but what it's going to do and how it's going to act, right?
The exact implementation varies a lot across research labs and industry use cases. For simplicity, let's anchor this in autonomous vehicles. The current world state is captured by the dashcam, either as a static image or a short video, and the intended action can be expressed as a text prompt like, take a left turn. Pretty much everyone agrees on this input shape. The debate happens entirely on the output side, and it comes down to one question. How faithfully should the world model represent the future world state? There are two schools of thought, generative and predictive or non-generative. A generative model outputs the future world state in a human-friendly form, like a fully fledged video. Such world models can be used as standalone tools, be it for synthetic data generation or interactive environments. Multiple prominent labs subscribe to this philosophy: NVIDIA, Google DeepMind, and Fei-Fei Li's World Labs. In this chapter, we'll look at the implementation of NVIDIA Cosmos as a representative model for the generative family. We'll also visit the other two in the applications chapter. NVIDIA Cosmos is a family of open-source models highly focused on physical intelligence, including self-driving cars and autonomous robots that can operate in a warehouse or even in a surgery room. Officially, Cosmos is a collection of models that includes Cosmos Predict, Transfer, and Reason. But technically, Cosmos Predict is the only one that abides by the strict definition of a world model. Given this video of a robot pouring the coffee, which is the current state of the world, Cosmos Predict outputs the natural continuation where the coffee kettle is angled back up in a vertical position. The other two Cosmos models are technically not world models. Cosmos Transfer is, well, a style transfer model, and Cosmos Reason is a visual language model, or VLA, that can answer questions about a given visual input. Nonetheless, you will hear people referring to all of them as world models, but we'll just have to live with this ambiguity in colloquial language. Cosmos Predict, the true world model of the family, is mostly a standard video diffusion model with a few tweaks. I have an entire YouTube series on diffusion models, but here's the high-level idea. The model architecture is a typical stack of diffusion transformers, or DITs, which I've covered in this video. The DIT is basically an extension of the original language transformer, capable of processing both image and text tokens. The current world state is compressed by a visual encoder into a smaller latent space, one slice for an image input or multiple slices for video frames. The visual encoder is an off-the-shelf model, in particular, the WAN 2.1 VAE encoder from Alibaba. These latent input frames, depicted in yellow, are concatenated with placeholders for the future frames, initialized with pure Gaussian noise. The diffusion model refines them iteratively for a fixed number of steps, after which the added frames meaningfully capture the future. The clean output latent is finally passed through an off-the-shelf video decoder, also taken from WAN, which maps it back to pixel-based video frames. This denoising network is trained with a standard flow matching objective, which I've covered in a previous video. Now, from everything I've described so far, NVIDIA's Cosmos Predict matches the structure of a general-purpose video generation model, like VO3 from Google or CDance from ByteDance, the ones we normally use to generate AI slop, like food cannibalism or soulless Hollywood-looking movie trailers. So what's the difference then? How is a video-based world model any different? One of the main differentiators is the training data. General-purpose video generators are trained on any sort of video that labs could get their hands on. This includes real-world footage, but also things like video games, cartoons, or even slide deck presentations. In contrast, Cosmos was pre-trained on highly curated data.
We've got over 20 million hours of physics first data. We're really trying to make sure that the data coming in is curated and trained, grounded on physics. When we train on this, then we evaluate it on a whole bunch of benchmarks that also check for that.
Cosmos Predict also makes a few architectural tweaks. For instance, it swaps out the standard off-the-shelf text encoder with Cosmos Reason, the visual language model from the same family. Normally, Cosmos Reason takes in an image and a text prompt, but in this particular setup, it will only exercise the text processing path. Just like the other models in the family, Cosmos Reason was also trained on highly curated data. NVIDIA even built a manual ontology around foundational physics, time and space, and made sure the training data covers it comprehensively. Compared to general-purpose text encoders like T5, this makes Cosmos Reason embeddings extra sensitive to the difference between the egg cracked after being dropped versus the egg was dropped after cracking. At a token level, they're very similar, but a physics-aware text encoder will produce meaningfully different embeddings. In practice, generative models work very well. Outputting pixels is actually inevitable if your ultimate goal is visual content for human consumption, like the interactive environments we'll see in the applications chapter. But when the output is consumed by an autonomous agent, it can have a more abstract representation. This is the predictive school of thought. Its biggest proponent is Yann LeCun, a Turing Award winner, former chief AI scientist at Meta, and current founder of a startup building world models. His philosophy is that an effective world model should not get bogged down into details, but rather discover high-level patterns that capture the fundamental laws of the world. In this view, A generative model can get distracted by irrelevant pixels. For instance, a road is the same road during the day and at nighttime. These two world states should live extremely close in a conceptual space, but their pixel representations are very different. But wait a second, modern diffusion models, including Cosmos Predict, do operate in a compact latent space. How exactly is the second school of thought any different? To answer this question, we'll look at Jan LeCun's work at Meta, in particular, a world model called VJEPA 2AC. It's a mouthful, but we'll break it down. You might have already heard of JEPA, which stands for Joint Embedding Predictive Architecture. LeCun proposed this conceptual architecture in his well-known position paper back in 2022. He argued that reconstruction losses like next word prediction in LLMs or denoising pixels in diffusion models are fundamentally limiting and cannot lead to true intelligence. JEPA is a modality-agnostic philosophy, which was later adapted to image, video, and even language. VJEPA stands for video, which is the most relevant for world models. In its raw form, VJEPA itself is not a world model, but rather a video encoder model. It takes in a video and outputs a latent representation for it. However, VJEPA can be fine-tuned into a proper world model, like VJEPA AC. AC stands for action conditioned, because compared to the base model, it can take in an action in addition to the video input. Under the hood, VJEPA AC puts together the pre-trained video encoder and the new predictor module. The predictor module takes in the current state of the world in latent form, as well as the action, and outputs the future in the same shape. To understand how this representation is different from the latent space in, say, diffusion models, it's worth understanding how the base VJEPA encoder is pre-trained. It's entirely self-supervised. The input video is corrupted by masking large regions within each frame, and the model has to recover them. But crucially, not in pixel space. The masked frames are passed through a context encoder, and the original frames are passed through a target encoder. Both are mapped to a latent space. Then the masked latents go through a predictor, which adds back the missing information. The loss minimizes the distance between the recovered and the original latent frames. If implemented naively, the latent space can collapse into something trivial like all zeros. This is in fact the biggest challenge in JEPA models. At a high level, the trick is that these two encoders are tied together. The target encoder is a sort of slow-moving average of the context encoder weights and doesn't get updated by gradients. But regardless of these implementation details, what I want you to take is that the reconstruction no longer happens in pixel space, but rather in embedding space. The loss is literally defined in terms of embeddings. In contrast, the latent space in the video diffusion model is more of a computational efficiency trick to manage the high dimensionality of videos. Ultimately, the training loss is still defined at a pixel level, which is less likely to induce a robust world model. So now you have a high-level understanding of what world models are and the two schools of thought for how to implement them. It's time to see how they're used in practice. What's the most common use case and the flagship industries that are using Cosmos-like models today?
The primary reason a lot of companies are coming and using and building off of this is because it's just really hard to get the data. If you think about, a self-driving car, most people watching will understand, right? I'm driving down the road, I've got a dash cam, I can see it. But there's so many different roads and so many different scenarios and different places in the world that you just can't record all of it. And so building synthetic data to help augment, like we talked about with that bear, or if you want to go to a different city or change the signs, you really need to build a lot of synthetic data. And if you imagine cars having dash cameras and there's a lot of it, think of a robot that you're building for the first time and you've only got maybe 100 or 1,000 hours of a robot just doing some simple thing because it doesn't exist yet. You're still building the grippers, you're still building the arms and the cameras, etc. So this is where having a world foundation model to help you extend your data is a really big deal.
So world models have many applications, but we'll look at three main categories. The first one is what TJ described, synthetic data for training and evaluation. Historically, the autonomous vehicles industry used procedural simulators. These were hard-coded virtual environments built on traditional game engines where every physical rule, visual asset, and traffic scenario had to be explicitly programmed by developers. They offered full control but were not visually realistic. Video-based world models trade off some of this controllability for near-perfect realism. Take Wayve, for example, a self-driving company based in the UK. They developed a series of world models called Gaia, for which they released quite comprehensive technical reports. Gaia can augment dashcam footage. Given a recording from a real ego vehicle, here captured by 5 cameras at different angles, it can produce synthetic variations. Some are changing the time of day and therefore visibility. Some are adding new obstacles, like this second bus that only becomes visible after overtaking the first bus. Augmenting all these scenarios increases the amount of training data and makes the model more robust. The specific color of a car might be irrelevant information for predicting its next move, but this irrelevancy only becomes clear to the model when it can observe that gray, red, black, and white cars behave similarly. Synthetic data becomes even more crucial in safety-critical scenarios. There's an entire taxonomy of stress tests that can be covered this way: car-to-car front turn across path, car-to-car rear stationary, and who knows how many more. Having such rigorous and comprehensive benchmarks allows AV companies to test how their vehicles react in life-threatening situations. Using world models to generate synthetic data for AVs is slowly becoming an industry standard. Google's self-driving car Waymo announced that they're leveraging a fine-tune of Genie, the world model coming from DeepMind, for similar purposes. But in addition to video, they're also generating LiDAR data, which gives their autonomous driver a better sense of depth. Synthetic data generation is an offline process. Once the dataset is produced, the world model is put aside and completely decoupled from the deployment of the autonomous vehicle. But as world models are becoming faster and faster, they're starting to be used in real time and interactively. Google's Genie is an experimental project that lets you craft an interactive 3D world from just a text prompt. It's what I use to generate the more sane version of a car drifting on an icy road. Genie is less focused on embodied AI and can create fictitious virtual worlds as well, like this one made out of felt. For about 60 seconds, you can use the WASD keys to move your character around, or the arrow keys to change the point of view. Throughout this exploration, the environment mostly stays consistent. And you can also create your own world. My virtual office here looks pretty convincing, even though there are a few unnatural choices, like my desk or the same orange painting showing up multiple times. Nonetheless, this technology is truly unprecedented. There's no doubt that eventually this will disrupt the gaming and filmmaking industries. But at this very moment, unit economics are still a bottleneck. Genie is only available under the Google AI Ultra plan, which costs $250 a month. Plus, once your world is created, you're given a single minute to explore it. This might be Google's way of keeping costs under control, but it also signals a technical limitation. To maintain consistency, the model must keep a memory of the entire session. Cross-frame consistency is actually one of the most striking aspects of Genie. Unfortunately, we don't really know how it works under the hood. Google published a technical report for Genie 1, but that's more than 2 years old by now. There's speculation online that the architecture of Genie 3 might have finally gone beyond the traditional video diffusion model, and the output might be more than just pixels, perhaps an actual 3D mesh and texture. But from Google's blog post, that seems very unlikely. They say consistency is an emergent capability and explicitly exclude 3D-specific outputs like NURBS and Gaussian splats. This is quite an opinionated choice and goes against the intuition of some experts in the field. Fei-Fei Li, the godmother of AI, coined the term spatial intelligence, referring to the ability of machines to perceive, reason about, and interact with the 3D physical world. Fei-Fei Li has recently founded World Labs, for which she raised over $1 billion. Their main product is Marble, a world model that's similar to Genie and offers an interactive experience in a virtual 3D world, but with a different technical approach that doesn't directly generate pixels. For interactive environments, pixel outputs have one huge drawback. They tie together geometry with appearance. This is different from classic game engines, where the structure of the object is defined by a three-dimensional mesh, while visual appearance, including color, roughness, reflectance, and so on, is applied separately via materials and texture maps layered on top. Marble brings back this decoupling, but in the form of Gaussian splats. These are semi-transparent, colored ellipsoids with their own size, position, and orientation. Since these aspects are decoupled, they can be controlled separately. World Labs even released a custom renderer that converts Gaussian splats to pixels, but also allows these massive virtual worlds to be compressed and streamed progressively, much like a high-definition video buffer. At this point in time, World Labs seems to be the furthest ahead in disrupting the gaming and filmmaking industry. All the world models we discussed so far acted like content factories, either generating synthetic data offline or creating interactive worlds for humans to explore. But at its origin, a world model, or rather small-scale model as it was called back in 1943, was defined as a neural component that actively helps humans make decisions. In this final category of applications, we'll look at world models that help agents in a similar way by unfolding hypothetical futures, either during training, inference, or both. At training time, an agent can practice inside the world model before deployment. This is particularly helpful when interacting with the real world can be expensive, dangerous, or slow. The umbrella term for this is model-based reinforcement learning, or MBRL. In classical reinforcement learning, an agent learns to achieve a goal from experience by interacting with a real environment that provides rewards for its actions. The main decision maker is the policy model. But in model-based reinforcement learning, there's an additional world model, separate from the policy, that can emulate the real environment. This was actually the design behind the paper that popularized world models, published in 2018 and titled simply World Models. They built a small agent to play an adaptation of the iconic game Doom called VizDoom, where the simplified goal of the agent is to survive for as long as possible. They enforced a deliberately strict constraint. The policy model should be trained without any interaction with the real game environment. Such interactions would only be allowed for training the world model. Of course, this is not a practical constraint in video games, which are relatively cheap to run, but at the time in 2018, it was a promising proof of concept that could one day materialize for training physical robots. So the VizDoom agent went through 2 training stages before deployment. First, training a world model. They started with a randomly initialized policy and played 10,000 games. In other words, they issued random actions until the agent got killed 10,000 times. In the process, the world model got to observe the reaction of the real environment and recreate a smaller, compressed version of it, where action consequences unfold in a latent space instead of pixel frames. Once the world model was trained, it was then frozen and used as a simulation environment to train the policy model. At the end of this second training stage, the agent was deployed in the real environment and was able to successfully play VizDoom, despite never having seen the actual game before. Subsequent research scaled MBRL in various ways. For instance, the Dreamer model family from DeepMind worked their way up to mining a diamond in Minecraft from scratch. This had been an unsolved problem in AI for years, and prior attempts needed human gameplay videos. And today, we're starting to see it applied to embodied robots as well. For instance, World Gymnast is a tabletop manipulation robot that was exclusively trained inside a world model and deployed on physical hardware without any real-world fine-tuning. In the example so far, the world model is a training time tool, discarded once the policy is trained. But world models can also stick around at inference time. The agent can actively use them in real time to unfold the effects of multiple candidate actions and pick the one with the most promising outcome. This is real-time planning. The most common planning paradigm for agents is model predictive control, inspired from 1970s chemical engineering. Here's one way to implement it. Before taking an action in the real world, an agent builds an entire tree of possibilities rooted in the current world state. The edges are candidate actions, and the nodes are hypothetical future world states as computed by a world model. It's like being inside the mind of an extremely anxious person, trying to foresee how the future might unfold. After building this tree, the agent identifies the branch with the best estimated outcome and performs only the very first action in the real world. It then throws away the rest of the branch and builds an entirely new tree rooted in the updated world state communicated by the environment. Working in a latent space is extremely important for speed since decision trees are built in real time. This is the idea behind mu0, a 2019 algorithm from DeepMind trained to play board games and Atari video games. But planning is now coming to embodied AI as well, like JEPA AC, the model we discussed in the implementation section as an exponent for the family of predictive world models. Technically, JEPA AC has a branching factor of 1, but follows the same principle of model predictive control. Interestingly, it uses subgoal images provided by the environment to judge how good a certain branch is. This means it doesn't even need rewards like the ones in reinforcement learning. You just show it an image of what you want and it'll do it in a task-agnostic way. On the one hand, this is Black Mirror stuff. But on the other, imagine how helpful this would be for an autonomous vehicle that needs to make a quick, critical decision.
You can start doing closed loop scenarios where you can start saying, okay, if I want to drive the car and turn right, what will happen next and what will I see? Now show me 50 different versions of that and then pick the most, useful or reliable one.
Before we wrap up, I want to mention that world models don't have to be visual. The same definition, given a state and an action, predict the next state, works in any environment where you have well-defined states and actions. A nice recent example is the Code world model from Meta. The world here is a software environment, a repository, a program, a terminal. The action is something like a pull request. And the world model predicts the next state, variable values, output, execution traces, and so on. So why not just execute the code and observe its effects instead of building a world model of the software environment? Well, it might take a full hour to run the entire test suite, and certain bugs might only surface in production, going unnoticed during development. A world model could be quicker and could catch potential issues without causing irreparable damage. We covered a lot of ground, but I hope that the through line is clear. A world model predicts how a certain action will change the state of the world. There's a lot of ambiguity around this term because the interface is so general and can be applied across so many industries. If you want to hear more from TJ Galda, the full interview is available to my YouTube and Patreon members. Stay tuned for more videos on world models.